All right, section 4.2, video 2. So we've learned a little bit about the sums. We've learned a little bit about some of the specific summation formulas that we're going to need. So now we're going to try and put it into use. We're going to learn one more thing. We're going to learn some summation properties, which really shouldn't come as much of a surprise. It works kind of the same way that limit properties and derivative properties do, such as the first one. If I have the sum as I goes from 1 to n of k times a sub I, k is a constant. I can pull that constant out to the front of the sum and then take the sum of a sub I and then multiply the k in later if I need to and or want to. And sometimes that might be beneficial. Okay, just like with limits and with derivatives, if I have the sum or the addition of two different things on the inside, I can separate those. So I can take the sum as I goes from 1 to n of a sub I plus the sum as I goes from 1 to n of b sub I. And then I can do the same thing with subtraction. Of course, the main thing with subtraction is the order does matter. Got to keep it in the correct order. Otherwise, it is the same thing. One thing I will tell you, and it's going to take a little bit of getting used to writing that summation symbol quickly, you will get used to it. All right, so there's some properties that we will probably be able to use. Okay, so for number one, let's do an example. I've got the sum as I goes from 1 to n of I plus 1 over n squared. All right, so one thing you're going to have to get used to here is the variable that's changing in this case is the I. That's what I'm plugging the numbers into. So anything else that doesn't have I is technically considered to be a constant. The n squared in that denominator is technically a constant. So I can actually pull that n squared out to the front. I can write 1 over n squared, and then I equals 1 to n of I plus 1. Okay, I can use another property that says I have the sum of two things, I plus 1. I can separate those into two different sums. So I can make the sum of I plus the sum of 1. All right, so now we're at a point where I can use some of those summation formulas that I gave you on the other page. So if I take the sum, this thing right here, the sum of I, well, that was, if you remember correctly from the other side, that was n times n plus 1 divided by 2. And then the sum of 1, because 1 is a constant, would be that constant times n. So if I want to rewrite this, I can distribute the n squared, excuse me, the 1 over n squared, onto the inside of this thing. So let's see, distributing the 1 over n squared is going to give me n plus 1 over 2n squared plus n over n squared. And that'll simplify just a little bit. So let's see here, I can get rid of that n and that n and that one. So that's going to leave me with n plus 1 over 2n plus 1 over n. If I want to simplify this even further and put it into one common fraction, I would multiply the second fraction here by 2 over 2 so that I can get a common denominator. And when I do that, what I'm going to end up with is n plus 1 plus 2 over 2n, which is going to be n plus 3 over 2n. So that is the sum of I plus 1 over n squared as I goes from 1 to n. Now let's say that I want to use that sum to figure out, okay, so maybe n was 10. So this time, so I'm going to use this. This time I'm actually going to plug a 10 into here. Well, obviously I don't want to redo the whole thing and add up all these things from 1 to 10, plug in a 1, plug in a 2, plug in a 3. I don't need to do that. I've got the formula over here, which tells me for any n value what I can get. So if I plug in n equals 10, what I would get is 10 plus 3 on top, which is 13, over 2 times 10, which is 20. So I get 13/20. That's for n equals 10. But what if I want to do for n equals 100? This is definitely not one I want to add up the first 100 terms of. So I would just plug that into there. So what we would get is 103 over 200. That's for that one. And then if n is 1,000, same idea. It's going to be 1,003 over 2,000. And what you might have recognized there is as these numbers are getting bigger, these numbers are actually getting closer and closer to a specific number. Okay, and if you haven't figured that part out yet, give it some time and you probably will. But as I'm letting these n values get bigger, my results are ending up being closer and closer to a specific value. All right, let's look at number 2. So number 2 is simply the sum from 1 to 20 of 2i. Again, I could add up all 20 terms, or I could just use one of my formulas, simplify it real quickly, and then have the value. So what I can do is I can rewrite this, pulling the 2 out to the front, and then I know that the sum of I from 1 to n is going to be, sorry, rewrite the 2, it's going to be n times n plus 1 over 2. N times n plus 1 over 2. That's the sum of the first n terms. Well, in this case, n is 20. So literally, I could just plug 20 into n and n plus 1, but we're going to go ahead and simplify. The 2's will cancel out, and that would just give me n times n plus 1. But again, n here is 20. So it's going to be 20 times 21. And that's going to be, let's see, 21 times 10 is 210. Double that is 420. So there you go. 420 is the sum from I equals 1 to 20 of 2i. Again, you could have just done plugging in 2, plugging in 1, plugging in 2, plugging in 3. So you get 1 plus 2 plus 6 plus 8 and all the way up to 20. Could have done it that way. But this is probably shorter and easier. Okay, number 3, not quite as short of a problem. We're going to do the sum. Oh, I guess I probably should have written on here. This should be I equals 1 to n. Not sure why I didn't put that on there. I equals 1 to n of 1 over n cubed, I minus 1 squared. Again, remember that the I is the only thing that you're plugging numbers into, so the 1 over n cubed can be brought to the front. And then I've got I minus 1 squared. Okay, so what we're going to need to do is we're actually going to need to FOIL that out. So we're going to need to FOIL out the I minus 1 squared. So we're going to get I squared minus 2I plus 1. That's what we're taking the sum of. So now we can split all those pieces up. So we'll get 1 over n cubed times. Splitting all those up, I've got the sum of I squared. I equals 1 to n. It gets kind of tedious to write all these. So I'm going to do the next step in one piece. I've got a minus 2i, so it's going to be a minus. I'm going to bring the 2 to the front of its sum, so all I have left in there is an I to deal with. Okay, you could have written it as minus sum of 2i and then pulled the 2 out later. That's fine too. And then the last one is just the sum of 1. I goes from 1 to n. All right, so now we have everything that we need to go ahead and use our formulas that we got before. So I have 1 over n cubed. The sum of I squared was n plus 1, 2n plus 1 over 6. That was I squared. Minus 2 times the sum of I, that's n n plus 1 over 2. And that looks like an I. It's probably because what I wrote should be a 1. And then the sum of 1 we know is just n. So then I'm going to go ahead and simplify some things and distribute the 1 over n cubed. So when I distribute the 1 over n cubed, okay, what we're going to get is n plus 1, 2n plus 1 over 6n cubed minus, those 2's are going to cancel out, so I'm going to end up with n plus 1 over n cubed, and then plus n over n cubed. That's distributing the n cubed. Now we're going to simplify. So it looks like I'm going to be able to get rid of an n on every one of these. That'll become a squared. That'll become a squared. That'll become a squared. That's nice. So what I have now is n plus 1, 2n plus 1 over 6n squared minus n plus 1 over n squared plus 1 over n squared. So I think if I'm going to simplify all these things, I'm going to have to do some foiling, and I'm going to have to change the denominators to all be 6n squared. So I'm going to FOIL the top of the first one. So that's going to give us 2n squared. Let's see, 2n and n is 3n plus 1. I'm going to have to multiply the numerator and the denominator of each of the other two by 6. So that's going to give me a 6n plus 6, so minus 6n plus 6, and then plus a 6 all over 6n squared. And then the last thing we're going to do is combine like terms. So we're going to get 2n squared. I've got a 3n minus 6n, so that's minus 3n. We're going to have 1 minus 6 plus 6. So it should just give us plus 1 over 6n squared. And that is the sum. So again, that one took a little bit longer because I had more pieces to deal with. And there's a bit of algebra in there as well. But that is the sum from I goes from 1 to n of 1 over n cubed times I minus 1 squared. All right, so we've got a couple more examples to do for this in particular type of stuff. So again, remember that the I is the only part of this that you're actually adding anything up. The difference here is now we have a limit. We're throwing the limit out in front. So now at the end of all this, we actually have to evaluate a limit. So let's do everything else first. The limit's the last part. Okay, it's the outside part. We're still going to do it, but we still have to write limit every time. So it gets a little more tedious because we have to keep the limit in there. All right, so the first thing I can see is the I on top is the only piece right here that's actually going to have anything added. The 2 times the 2 on top is a 4. That can be pulled out as a constant. The n times the n on the bottom one is an n squared. That's not having anything to do with our I, so we can pull that out as well. So I can pull out a 4 over n squared. Now make sure you see I cannot pull that to the front of the limit. And the reason I can't pull that to the front of the limit is because the n is in the limit. So I could pull the 4 out if I wanted to, but the 1 over n squared must stay after the limit because I'm actually taking the limit of an n squared or an n piece. And then I've got the sum of I. Okay, and we know what the sum of I is. We've used that one several times. So let's see, we're going to have 4 over n squared times the sum of I is n plus 1 over 2. Okay, let's do some simplification. Actually, we don't even need to do some simplification in this case. So let's look at this. Now we're taking a limit. We found the sum technically. We didn't simplify, but we found the sum. Now we're looking at the limit as n approaches infinity. Remember, what you're looking at is the growth rate on the numerator and the denominator here as n approaches infinity. Well, if you're careful, if I were to distribute, which I don't have to do, if I were to distribute, the n times the n up on the top here would give me an n squared. That's my highest growth rate on top. The highest growth rate in the bottom is going to be that n squared. So really what I need to do is look at divide the leading coefficients, because these two things have the same growth rate. Well, the 4 would get distributed to here and be a leading coefficient. The 2 would get distributed to here and be a leading coefficient. So I would get 4 over 2, or 2. So that would be that limit. Okay, let's try one more of those just to make sure that that hopefully makes some kind of sense. So we'll have the limit as n goes to infinity. Again, I can pull anything that doesn't have to do with the I out to the front. So I'm going to pull out a 16 over n squared. Sum of I goes from 1 to n. Again, we just did the sum of I, so we can do it again. So 16 over n squared, the sum of I is n plus 1 over 2. Now again, on the top, we're going to have an n squared as my highest, so the coefficient there is 16. N squared is the highest in the bottom, so the coefficient is 2. 16 over 2 is 8. And that's your limit. All right. I believe that's all for those. All right, so we're actually going to come back with another video and actually do some more formulas and calculate definite integrals.